So my name is Diya Naik, and I'm from New Albany High School, and I will be discussing my meta-analysis project, analyzing nuclear size trends in isotopes using proton elastic scattering and differential cross-sections. So my scientific question is, does the change in radial size of the nucleus directly correspond to the change in number of nucleons according to volume? Or do factors other than the change in volume influence radial size? And so my hypothesis is that a change in the number of nucleons changes nuclear radius by a cube root of that radius, which would be aligned with the volume of a sphere equation. This hypothesis is chosen because nuclear density is around constant no matter the type of isotope, so I would assume that this relationship holds. So for some background on how I am going to prove this, I will be using elastic nuclear scattering data. So scattering experiments are basically when a particle is collided with a subject being scattered. In this case, we're either colliding protons or neutrons at a sheet of nuclei, so that might be carbon-12 or oxygen-16 or helium-4. And the way that the proton or neutron deflects based on the charge and mass of the nuclei can tell you about the properties of the nuclei itself, including stuff like nuclear size. The differential cross-section is the number of particles that deflect at a certain solid angle for time, and it's basically differential cross-section explains how that deflection happened. And a graph of differential cross-section versus scattering angle, you can find out different properties in the graph, such as dips, and they can be used as a benchmark to compare different energy level experiments with each other, and it is related to nuclear size, basically. And so these graphs, where these dips occur, the angle where that occurs, can be used to indirectly find a relationship with nuclear size. And so I find these graphs by using a self-developed Python program where it takes data from the National Nuclear Database Center, and it basically goes through and finds the energy of these differential cross-section experiments and their scattering angle, and graphs a log version and a regular version of it. So, as you can see here, it shows the energy level as well as the properties of the graph. And it's the log graph that is used to find the dips because it's easier to find on a log graph than on a normal graph. So, next, because we can't directly compare the number of nucleons with the nuclear radius, because the nuclear radius can't be directly determined, we're going to use an equivalent relationship to test this hypothesis. And also because we're working with experimental data that has energy levels that vary from each other, we need that to be factored for. So that's why we use this sine theta versus wavelength over the cube root of the number of nucleons, represented by A. And this might sound really complicated, but essentially it boils down to two equations that are manipulated to form this. So there's the Compton effect, which is when something of a certain energy and therefore a certain wavelength is scattered towards something, you can find the width of whatever aperture or whatever nucleus, in this case the size is, through the wavelength. And we can find wavelength using the relationship between energy found in MeV and the wavelength associated with that. And so using these things together, we can therefore find that this sine theta versus wavelength over the cube root of A relationship essentially functions the same way as a cube root of, it basically proves the same proportion as a cube root of number of nucleons and nuclear radii. So they basically prove the same thing. And so if the scatter plot for the sine theta versus wavelength over the cube root of A is linear, then it indicates that this is the result of volume and not any other factors, and that is how we will be able to prove or disprove our hypothesis. So the methods I used is, like I mentioned before, I used this self-created Python program where it takes this data it takes text file data of this from the nuclear database, scattering experiments, and it collects the data it needs, It and then the criteria used to find which data points can be used are it's from 50 to 200 mega electron volts. The only nuclei we look at is carbon, oxygen, and helium. I tried to look for different types of isotopes, not just carbon-12, but also like carbon-13 or carbon-9. But for the most part, there was only carbon-12, oxygen-16, and helium-4 nuclei that were like usable by the previous criteria. There was one carbon-13 point though. Meanwhile, there's only proton elastic or neutron elastic scattering for the purposes of this, and there had to be variable angles, and there had to be more than 20 data points per data set, because otherwise it would not read it would not develop enough of a dip, or like a significant enough dip for it to be recorded, or there were like false recordings of that. So that's why more data points that are needed. So here are the data tables from, here's the raw data where it's like the energy and the number, the angle, the scattering angle, and then using some calculations, we can solve for sine of theta and the wavelength over cube root of a, and therefore we can create a scatter plot for that. And here at the bottom, you can see the sample calculations I did for that for the first data point, and I just did the same thing all the way down with an Excel spreadsheet. What's really useful about the scatter plot is we can see the r-squared value for the linear approximation that is made, and by examining the r-squared value, we can see how well it matches the hypothesis. So the scatter plot, as I said, there's a linear line of best fit, and the r-squared value is 0.54. So 0.54 is a really low r-squared value. R-squared values basically are the amount of variation from the line of best fit the data points have, and it's from a scale from 0 to 1, with 1 being the most like linear, and the closer you are to 1, the more linear it is. And 0.5 is very low, so a linear graph does not fit the data, which means that the change in volume, the change in number of nucleons, is not enough to explain the nuclear radius, and there must be other factors at play. As you can see here, the scatter plot data, it does not look very linear, and the linear approximation doesn't work as well. So here are some potential sources of discrepancy. It might be due to quantum uncertainty. So basically at really, really tiny scales, size itself is not like a defined thing because of Heisenberg uncertainty. So, and since these lighter nuclei are so small, it might lead to more inconsistent size calculations. However, this is a less favored explanation because we use multiple data sets, like more than 40 across varying energy levels, so it should account for the inconsistencies. Meanwhile, neutron skin might be a more plausible explanation. Neutron skin is the difference in size between neutrons and protons, with neutrons being bigger, and the more nucleons there are, the more of an effect the neutron skin would affect calculations. So if there's this discrepancy, that means there's a smaller nuclear radius, which means it's a larger scattering angle because those two variables have an inverse relationship. And so if there's a larger scattering angle, when we go and calculate that, it leads to a smaller sign than expected, which is what we see here, is that it appears that there's an underestimate. So it matches the finding that the graph's linear approximation, sorry, I said that wrong. It matches the finding that the graph's linear approximation is an overestimate because it's a smaller sign than expected. However, there were some experimental flaws with this meta-analysis. There's a lack of variety in isotopes per element. Well, it's only carbon-12, oxygen-16, and helium-4, which are the most common of their element, but it would have been more beneficial to have things from a wide variety of isotopes to expand on this relationship and make sure there's no variables we're not accounting for. Also, there's no neutron scattering data was usable. I looked through the data sets and most of them were not, and they were basically unusable because they didn't have enough data points, or they were not the right type of data where there's no variable angle. And it's really useful to have neutron scattering data instead of just proton elastic scattering data, because neutron elastic scattering data would reduce error because neutrons and protons interact with nuclei slightly differently. Using multiple methods to arrive at a relationship would reduce error. The ramifications for this difference in nuclear size and how it's not entirely explained by volume affirms the need for more research in exploring the density of nucleons themselves, because it ties into ideas like neutron skin or why is this relationship not exactly right. And there are two major methods scientists explore the density of nucleons, aka protons and neutrons, with, and it's with the nuclear density functional theory and ab initio theory. The former is used for larger isotopes, and it's more grainy and less precise. Ab initio uses actual Schrodinger equations and is really, really precise. And merging these two approaches can create a more detailed view of the nucleus, which can be used for modeling, and then those models can be experimental data, like those graphs I showed you earlier, and this can refine nuclear models. So experiments like these are really important for those reasons, and expanding on the experiments is also really important. The exact size of the nuclei important. So another place where this is really relevant is in astronomy and with neutron stars, because the exact size of the nuclei is normally not important in our everyday lives, but it is really important in nuclear dense environments such as neutron stars, which are created when there's enough pressure to be as neutrons to be as close together as possible, because the force of gravity crushes a star, and the neutrons are so close together as they possibly can be according to the laws of physics. And because the nuclei are so close to each other, accurate size constraints on them in turn constrain the size of the star, and it can be better used to understand the properties of neutron stars, and therefore physics at this extreme level. Some future experiments that we can conduct to expand upon our findings is we can conduct a meta-analysis of data from other databases, not just the very specific subset of National Nuclear Database data I took from their X4 data. To take from other databases that have substantial amounts of both neutron and proton elastic scattering data, and use larger data sets and more of them. And another idea might be to examine the deviation from linearity for lighter versus heavier nuclei, and see if that deviation can be explained by neutron skin, because, as I said, heavier nuclei should have more an effect than lighter nuclei. But other experiments would have to be done to make sure that's the reason, or to explore any new origins or other conflating factors. Thank you so much for listening, and that was my project. Thank you once again.